Okay. Good morning. Thank you for coming. Appreciate it and appreciate the opportunity. Come on in and have a seat.
I'll sit back here because I gotta.
We're live. They're recording this, so we will see how it goes. The first time I've done this particular one. But my name's Larry, K3KA. I am one of the section ARRL technical specialist. Been a ham since 1964 and done a lot of teaching of classes and exams and a lot of stuff, and spent 48 years with the Coast Guard in the technical field, electrical engineering, electronics, communications, radar, navigation, teaching that as well as running the maintenance group. So this is going to be basics. Remember the basics, where I come from, and this is not to compete with the high tech, because we get wound up in these things, but we need to remember the basics to understand what's going on now and how to help future hams, how to help out the young hams. Okay, you got questions or stuff, please speak up. I can't guarantee that I'm going to have all the answers to everything, but another point in here is that you don't have to know all the stuff, but having an idea of where to find it or who to find it from helps. Excuse me. Okay. Started with just what to call this, what to do about this. And excuse me, let me get some. I got some copies of this presentation here. There's 2 pages, 8 slides on the 2 pages. If you just what to call this. I went through back to the basics, remember the basics, and what are the basics and why. Don't forget. You know, we talk about stuff, but it's not always simple, but yet there are basics to it. And how many times do you make things work by making sure that the OFF switch is in the ON position, right? I mean, it sounds like, well, duh, but sometimes you get wrapped up and you got to go back there. You got to make sure. So we don't want to forget the foundations, including not only the electronics and the specific part in the theory, but also the rules and regulations. Where do things come from? So. And I mentioned earlier to a couple of you about, at 14, I passed the code test and I passed the theory test and got my ham radio license, but I couldn't get my halfway dipole to work. You know, didn't know how to tune it. Didn't know what loading the thing was. So we have to go back and create an atmosphere that we can help people that are new to amateur radio, or that want to be interested in amateur radio, and that also, hey, remind the seasoned guys about what's going on. I take part in the Thursday night technical net on the NI4CE system. Thursday nights at 9 p.m. I'm on there, and most of this stuff I'm talking about has come up on that net in one form or another. And I mentioned basics because I've been on there with very seasoned hams, and then with very new people. Some of the things to talk about, we'll get through here. Rules and regulations, Part 97, the Communications Act of 1934. Scientific principles, something about some assumptions, isotropic isolator, a dipole, speed of light, formulas that are handy, nice to know, Ohm's law, wavelength frequency relationship, distance to the horizon, and how to calculate how long to make your dipole antenna. Some formulas. Mr. Ohm said that there was a relationship between the voltage across and the current through a device, resistance. So we're going to expand that a little bit to impedance. Okay, DC, AC, and impedance. Distance to the horizon. Y, line of sight communications. And how to make your dipole. Antennas. Measurements are relative to wavelength. Okay, we'll touch on that touch more in a bit. Impedances and gain, and a little bit about directivity. And for seasoned hams, don't forget, remember what it was like as a new ham or coming up. Why amateur radio? It's laid out in Part 97 of the FCC rules. And I mentioned the TechNet, because one night we was on the TechNet and somebody asked a trivia question of where are the basic rules of amateur radio. Of 18 people on the net, two people knew it. Okay? That's pretty basic. We're running amateur radio. There are specific rules, regulations, you know. What frequencies can you operate on? What modes can you operate? What power? What are the power limitations? Emission types, and safety. That's all part of it.
Where did you say that was located?
Part 97, FCC rules, Part 97. And the basis of that is the Telecommunications Act of 1934 as amended.
47 CFR 97.
97, yeah. There you go. You got it. Thank you. Appreciate that. Okay. Looking at slide 4. I call it science. Maybe it's not the good thing, but we make assumptions in our formulas. What are they? Operating in free space is a common assumption. The speed of light in free space, okay, or the isotropic emitter, which is a point in free space that emits equally in all directions. It emits like a sphere. And we use that as a reference, but that's an assumption. The dipole is a basic 2-element antenna. We're going to talk about that a little bit more because we go from the dipole and then we go to a vertical, and it's really a form of a dipole. And I had an extra ask me, he says, I gotta check that because I don't understand that. So it's not perfect. Think about things as perfect conductors. They're not. The Earth is not a perfect sphere, and on top of that, it's not in free space. I mean, we're down to operate in space. You got the atmosphere. You got objects in proximity. Okay, you got vegetation, buildings, different things. You got hills, so it affects that. Wires, and even wires. We talk about them, we think about them, we calculate things, but they're not ideal. They got resistance, and their velocity of propagation on a wire is different than free space. Okay, if we go to slide 5, a couple little formulas here. Ohm's law. We talk about Ohm's law, Mr. Ohm, and said that the relationship between the voltage across, if you got an element, whatever it is, the voltage across, the EMF, and the current through it, I, are related by the resistance. E equals IR. Of course, you can write that in 3 different ways, but you don't have to remember it. You just got to know one. Okay? And from that one, you can get to the other 3. Or if you're a visual person, you draw the pi and what? E equals IR. I equals E over R equals E over I. You know, if you're a visual person and not an algebra person, you got ways to, easy ways to think of it, remember it. What's one of the other formulas? Oh, I talk about power, E equals IR, E equals I. Voltage times current equals power. I mentioned resistance in wires earlier. Why are we concerned about current and resistance in wires? Current through resistance wastes power. It goes up in heat. You ever wonder why TECHCON transports electricity at 100,000 volts? What happens when we raise?
Loss is less.
Loss is less. Why is the loss less?
Travels on the surface of the conductor instead of through it. One thing.
As we go up in frequency, yes, sir. Okay? But the biggest thing about loss over long distances is that loss power, if you do that, is I squared R. So as I goes up, the power wasted in that resistance in that wire is by the square. So if you raise the voltage on the wire, you're reducing the current substantially, and by the square, you reduce the power lost in that wire. And when you're talking, how many megawatts does TECHCON, and TECHCON's a relatively small company, how many megawatts do they transmit over these wires? A bunch.
Millions and millions.
Millions. So you reduce that current, you're reducing the loss in the wires. Not necessarily related to, specifically to ham radio, but it affects us personally. Let's see, what else do we have here in terms of wavelength? Wavelength in meters. 300 approximately 300 over the frequency in megahertz. Because we took out the 10 to the 6th. I say approximately because actually the speed of light in free space is 299.79 or something like that, million meters per second. Okay, 300 is easy to use. And it comes in handy, the relationship between wavelength and meters. Okay, 300. So you got 10 meters is going to be what frequency? 30 megahertz. Okay? And this comes in handy because we talk about the bands in terms of meters quite often. How long are they? What's on the dial of your radio? Megahertz. Now, but it's something to think about. Now think about that as a new ham and how do you explain that. Hey, and they're related by c, the speed of light. The speed of light in free space. Okay. Distance to the horizon. And we're interested in this because of why? VHF, UHF, and up. the radio waves don't bend much. It's essentially line of sight. So if you have the Earth and you got an antenna here, this horizon somewhere here. The general formula for that is the horizon in miles is the square root of 2 times the height in feet. The repeater at Boyette, 800 feet. 2 times that's 1,600 feet. The square root, 40. The horizon's approximately 40 miles. Okay, now if the antenna on the other end is your handheld at 6 feet, or on top of your house at 30 feet, then you get to add that distance to the horizon on as well. But the Earth is not a perfect sphere, and also there's vegetation which happens to affect VHF, UHF transmissions more than the HF. So they all impact the actual range. But that's, you know, you can figure roughly 40 miles, you know, even if your antenna's in theory on the ground. But you got to consider what's in proximity. Handy to have. Question on the net. The guy's got his antenna at 15 feet above the ground, and he's trying to contact this repeater 80 miles away, and he keeps saying, I want a bigger amplifier. I don't care how big that amplifier is. If you're here, you're not going to hear that guy. Now there is a little bit, you know, this bends a touch, a little bit, but not much. The only exception there is you will see sometimes here on the south, particularly in the south, tropic ducking. Sometimes it will follow storms, heavy storms, and different stuff, and then all bets are off. I sat in Cape May, New Jersey with my 2-meter antenna at about 15 feet above the ground, 13 element, and all of a sudden I'm hearing South Carolina, Georgia, and talking to them like we're talking here. All of a sudden I hear somebody in Connecticut, okay, coming in, and I keyed him up and I'm talking to him. He says, well, you're a little scratchy sometimes. I said, oh, you're off the back of my antenna. Because inversion, you get an inversion layer is what it is, temperature inversion, and it acts like a waveguide, and the propagation stays between those layers. But it's rare, but it's a lot of fun when you come across one. You know, so there is exceptions to these things. Okay, half-wave dipole. And why I pick half-wave dipoles, and part of this goes on to, I think, 6 as well. Yeah. Half-wave dipole. Why do we call it a half wave? Dipole because it has 2 elements, right? Okay. A half wave is because it's in theory the equivalent length, the total length is the equivalent of a half a wave. Now, how do we want to draw a half a wave? We want to draw a half wave this way? Or do you want to draw a half wave that way? Right? And why did I draw the differences?
They're both different points on a 360 degree or 2 radian, 2 pi radian
Okay.
oscillation.
Okay. This is half of the sine wave, right? Okay, that's where the half wave comes from. But think.
Half, that's,
Okay.
you could have drawn it upside down.
Okay. Yeah, you draw it.
Same thing.
Same thing. But why is this particular configuration? Why did I pick that particular configuration? What did we talk about a little while ago about E equals IR?
Oh yeah.
This is the current distribution, and we know that how? The end of the wire, we got no current there, it can't go anywhere, right? So that's the current distribution. E equals IR. Current is zero, near zero, which means the voltage has to be high. So this is the voltage distribution on that antenna. Okay? Electromagnetic waves. Did I mention that somewhere here? Okay, let's, before we get there, a couple more questions about this half-wave dipole. And half-wave is at relative to frequency, okay? So it's at resonance. What's the input impedance here of this half-wave dipole antenna at resonance?
Technically it's 70 ohms, but in reality, but for our use it's 50 ohms.
So somewhere in there, right? 72 ohms. And typically I start this with, wait a minute, what do you often feed this with?
50 ohm cable, so you automatically get a small
Yeah.
bump in
My dad running his SB 101 fed it with 75 ohm cable. Reduced the mismatch here, and the old radios didn't care. You had tuned output, so you loaded it anyway, so he didn't care. It worked fine at 75 or 50 ohms. Okay. What other forms of dipoles are there?
There's all sorts. Everything from off-center fed,
Off-center, off-center,
three halves wave,
off-center fed, and
full wave dipole, which is high impedance monster.
yeah, or like an end-fed,
Yeah.
end-fed half wave, right?
Well, yeah. And OCS,
but-
by moving it, you're just transforming the impedance.
Right, because you're feeding it over here. In
Yeah.
fact, I run an off-center fed dipole. My flagpole in front of my house is a vertical off-center fed dipole.
So you move the impedance up as you move the feed point out.
Right,
towards
the impedance goes up. Exactly. You know, what's the, okay.
Why would you want more impedance?
because you can easily match it with a transformer.
You can match it with a transformer, and it allows you to operate more frequencies. And sometimes that's all you have the space for.
Well, I have a full 80 meter center fed, and I get everything.
Yeah, 80 meters, yeah, will work good. But how are we coupling that to the transmitter? You know, this is part of one of the further statements on down the line, but it's relevant because we said this was, you know, around 70 ohms, or around 75 ohms at resonance.
Coax at 70 instead of 50.
They do,
So
but-
why do they always try and sell you the 50?
because 50 is the most common made one there is.
So it would work better if you switched it out for 70?
If you could find, you know, unfortunately, most of the 70 ohm coax comes from cable TV, and it doesn't typically handle the power well, but it's easier to make it. There's more of it made. Okay, so what do we?
75 ohm coax is just very expensive.
So if this is 50 ohms, and this antenna is somewhere around approximately 70 ohms, what do we call that point?
I call it an inflection point.
Okay, it's a discontinuity, whatever you want to call it, okay? It's a difference in impedances. Why is that important? The maximum power transferred when the input impedance equals the output impedance for maximum power transferred. If they don't match, what happens?
Generate heat.
You generate heat. Why? What happens at this junction when you've got this wave coming? Okay, and it says, oh, wait a minute.
You have phase mismatch.
You have mismatch, you have reflected power. What's not transferred is reflected. Comes back to your radio, and that ratio, SWR, standing wave ratio. And why is that bad?
Your transistors don't like it.
Transistors don't like it. It comes back to your rate. Okay? And also, you're not getting, you transmit 100 watts here, you lose a little bit in the coax because the coax isn't perfect, right? And then this is different, so you end up with reflected power. So you're losing more power. And unfortunately, it goes back to your transmitter. So what do we do to compensate for that?
Choke or balun?
Antenna matching unit.
Antenna matching unit. Okay, what do we often call them? Antenna tuners.
So they don't tune to the antenna.
They don't tune most of them do not tune the antenna because where are they located? They're down here with the radio, right?
Yeah, they make the radio happy, not.
They make the radio happy, exactly. My words exactly. They make the radio happy. They help protect the radio. But you haven't resolved this. You've resolved the issue to the transmitter, but you have not resolved the problem that's created here.
It's a mitigation device.
Yeah. Yeah. So what's a better solution?
Tune the damn antenna to.
Tune the antenna. How are you going to do that? If you got a single frequency, it's easy, right? You cut it or you make it that way to match it. But you're not. You're trying to run all bands on this one piece of wire, which is a good antenna. Okay. You put the matching network here at the discontinuity. That way you tune the output of this to the input of that device, you get maximum power transfer.
So if you had 70, if the coax handled 70, you'd never have SWR.
You'd have a problem between the radio and the coax.
But remember this is an 80-meter antenna. And when we're talking about antennas, we're talking about in relationship to wavelength. It's matched at 80, okay? So you got a 1-to-1 at 80, okay? But once you change to 40, you deviate to that, you're going to have a mismatch here. Now, typically third harmonics, you can use them on the third harmonic, and you say, well, instead of a half-wave dipole, I got a, three halves. But three quarters are not typically as good a radiator as a half-wave. Okay, they will load fine, yes, but they do not radiate as well, typically. But if it works, that's all we care about. You want the radio happy, and you want it to work.
That's the goal.
My off-center fed vertical, it's fed with open ladder line, 450 ohm open ladder line, to a matching device at the base of the antenna. But I still got a mismatch between here and the base of the antenna. But why do we use open wire feeder?
It moves the inflection point up and down the wire as frequency changes.
Yes, it tolerates high SWR very, very well. Not like a coax, it tolerates it very, very well. It really don't care. And also, it's really low loss. Okay? Why is it low loss? I guess we could get to transmission line types. Ladder line, open wire, coax, waveguide. What drives the loss in a coaxial cable? Heat's generated why? Resistance in it, right? Yeah, because we're typically measured in dB per 100 feet or something along that line. But what's a coax cable constructed of? Coaxial, here, the conductor in the middle. What's this stuff in here? Some insulation, some dielectric, okay? And that affects what part of the coax in terms of radios? This may be slide 8.
Another type of insulation affects power handling, but it also does affect loss.
Affects loss, it affects power handling, and what else does it affect? Velocity of propagation.
Oh, yeah. The
Okay.
VS goes down for certain coaxes.
Okay, I mean, so it can go down as low as about 60. And this here again is we're comparing this to free space. Okay, so a coax in general, not always, the denser the dielectric, the lower the velocity of propagation. Heliax has a very high, 90 some percent because it's mostly air, and they got a plastic or a insulator wound around it to keep the space, but it's mostly air. What about your twin line, your ladder line? It's air. Okay, so the velocity of propagation. Why is this of interest? How do we phase antennas? We want to run phased antennas. What do we usually use to, not maybe I shouldn't say usually, but what can you use to run antennas out of phase?
We can use phased, we can use coax.
Coax, lengths of coax. You want to run them quarter wave out of phase, you feed the second one with a quarter wavelength at that frequency, put it out of phase. How do you know what length that quarter wavelength is?
Multiply the frequency by the velocity factor.
Velocity factor. That's why the velocity factor is important, because the slower it is, the shorter you need to make that quarter wavelength piece of coax. Yes, sir.
No, I'm just,
Okay.
just making sure everything's right.
Yeah. Another thing about velocity of propagation, and we can go back to our dipole. How do we figure out how long to make the dipole? Frequency you want to transmit at. Okay. And what did we talk about?
And we calculate the
You calculate it out. So you take, in theory, the ideal situation, if you calculate half wavelength, and if we look at it in terms of feet, half wavelength in feet equals about 492 divided by the frequency in megahertz. But that's a wire, and it's not free space. What's the propagation of the wave on that wire? Is it at the speed of light? No, it's something slower, somewhere around 95% about. So in actuality, it's about 468 or 469? 468 divided by the frequency in megahertz. You still may. Insulated wire, you got capacitance, added capacitance to it, okay? How high is it above ground? Is it a half wavelength or more above ground? Probably not, especially not at 80 meters.
That's 25, mine's 25.
Yeah, see, so you got coupling to the ground, so that affects that affects the tuning. And was mentioned earlier about SWR. Okay, higher on the low end of the band or the high end of the band?
Maybe higher on the low end of the band.
Higher on the low end of the band, which means the antenna is too short? Too short, because you need more wire. Lower frequency, longer wavelength. Speaking of long wires, you hear a lot of people talk about long wire antenna. What is a long wire antenna?
Not cut to a specific frequency, or it's cut to a specific frequency that is outside the amateur radio bands for our purposes.
How do we know if it's a long wire? What's it relative to? Mentioned it earlier. Antenna measurements are relative to wavelength. The wavelength of 80 meters is what? 260?
265.
265, thereabouts?
Yeah.
People say, I got a long wire up. How long is it? 50 feet. That's not a long wire on 80 meters. It may be a long wire on 2 meters. You got to feed the long wire, but what's an advantage of a long wire? They're relatively easy to put up. You need a lot of room to put them up, because you need something over 80 meters. You need something over 265 feet. And you'd like to see 2, 3, 4, 5 wavelengths. Why? What's the radiation lobe of a dipole antenna?
It's broadside to
It's broadside, right?
yeah, very much that kind of.
It's actually like
Yeah.
this.
I was gonna say.
Okay,
Figure eight.
figure 8. So what happens when you feed this thing from the end? Even if it's a half wave, but you feed this end fed, got this long wire, okay? You feed it from here. Your lobe initially is going to look like the same figure 8, right? Okay. As this wire gets longer, you start forming lobes. And as you get longer and longer, those lobes converge together towards the end of the antenna. You will hear long wires being hot off the open end. That's why. As you go up in length, I mean, they're great antennas. And at the long wire, they're one directional, but boy, they're hot.
And that's why you point of average in the direction you want to hear.
Bingo. Okay. There's something else. Well, all your power, your big lobe is out here on the end. All these. No, I'm talking about in terms of transmitted power, or receive.
So then it'll send further.
Yes. Okay. Talking about that. Okay. Antenna gain. How do we generate antenna gain?
Some manufacturers, I think they use vanishing.
Well, you have to pay attention. You have to read the fine print.
Yeah.
Okay, you got. Remember the isotropic
DVI.
isolator or radiator, and this is a sphere. Okay. So when we change from that to our dipole, what happens to that sphere? It's no longer a sphere, right? It's this donut we talked about around the antenna. It's not equally in all directions. We've squashed it up into this donut. So the half-wave dipole, or you'll hear quarter-wave vertical, okay, the gain is about 2.1 dBi. 2.1 dB above an isotropic isolator. So when you look at these gain figures in the catalog, you got to pay attention to, are they saying dBi or are they just saying dB? dB should mean by default dBd, dB above the half-wave dipole or dB above the quarter wavelength. Okay, but something that's measured in dBi, to get to above a dipole, you got to take 2.1 dB away from it. 5/8 wave vertical. Advertised as a gain of what? About?
1.8.
Okay,
Yeah.
somewhere you will see a lot of different things. You will see up to 3. How they generate this gain? You got a vertical, right? And you got a lobe. Looks like that. Okay, quarter wave dipole, or quarter wave vertical. Okay, how do you generate gain? How does a 5/8 wave antenna generate gain over that?
I guess it artificially moves the feed point up. So even though you're feeding it at one, it artificially sets an inflection point up on the radiator itself. Would make sense to me.
Okay, so as a result of that, you change the current distribution.
Exactly.
Okay, and the current distribution represents the radiation pattern of the antenna. And instead of you get this great big lobes, you go to 5/8 and your lobes come out here, come out further. Okay, so 5/8, you will see up to 3 dB gain of a 5/8 wave over a quarter wave. Okay, 3 dB, but you will read in the advertisements, oh, it gives you 5.1 dB. dBi. You got to take the 2.1 away to get to the 3. Okay, but antennas do not generate more power. I mean, it's only got what's fed to it. It doesn't generate more power. You control the shape of the lobes, so power in the specific direction you're looking for concentrates it there. Okay, you're squashing this lobe into this lobe, generates the gain. Okay. Let's see, what else? What else haven't I covered on there? Anything, any questions? We talked about impedances of.
I actually don't have a question yet. We might want to go over with an OCF what happens if you move the feed point on a dipole away from the center to form those OCFs. I kind of understand it, but I think I need a little more.
Okay. Okay, let me one thing before we get there.
Okay.
I'm not sure I'm going to have your total answer, but we can find it. Okay. We talked about the straight dipole, okay? 70 some ohms. Quarter wave. Yeah, quarter wave, not half wave, quarter wave. What's the input impedance here of that? What are we feeding it with?
You're feeding it with
50 ohm coax. What's the impedance of that quarter wave when you got ground radials here at right angles?
Ooh, I know if it's a total vertical dipole, it's supposed to be about 90 ohms, so I'm gonna guess it's between 70 and 90.
It's around 37. Okay, it's around 37 ohms. Straight at 70 some, it's around 37 if it's flat. Okay? You'll see counterpoise, you'll see them on the verticals. They aren't at 90 degrees, are they?
48 usually.
They're at some angle.
Oh, yeah.
Then what's the impedance become? What's the objective of that? You want to get this towards 50 ohms, right?
So that's how the ground plane works.
That takes care of our mismatch. Okay. How the ground plane actually works, okay, is that, you believe me when I tell you this is a dipole? We call it a quarter wave vertical. You tell me, will you believe me when I say it's a halfway dipole?
Yeah,
Why?
because you have two quarter wave elements. The fact that they're not linear and lined up vertically or horizontally doesn't really matter. No different than
The ground plane creates a mirror image of that vertical. Now you have two-sided half-wave dipole. Okay. Anybody use folded dipoles? We said just the dipole, the impedance is about 70 ohms, 75 ohms, somewhere in there. What happens if you take and fold this wire back on itself? Some of you have been around long enough to know the 300 ohm TV antennas, right?
T2FDs, those T2 folded dipoles.
And you can even do this. So this was 70, say this is 75 ohms. If you've got two wires, the input impedance becomes 300 ohms. The square of the number of the wires, 2 squared, 4 times 75, 300 ohms. So you could feed this with 300 ohm open wire. If we went to 9 times 75 is what? 600?
665.
Yeah. So you could feed it with 600 ohm twin lead. And once again, why do we like open wire? Lower loss, and it tolerates it tolerates high SWR. Okay, off-center fed dipole. Had the question about that. Roughly, typically we put it at about what? 1/3, 2/3 off-center fed?
Yeah.
Something like that. Mine is not, because I use it from, I use it from 10 meters to 160, but somewhere 1/3, 2/3. So what do you want to feed this with?
Well, if you feed it with coax, you're going to have a severe mismatch.
Yeah.
So you usually use a unin.
Well, unin is 1-to-1.
Well, you usually use a
Tra-
4 to 1 or 9 to 1 transformer at the feed point.
Okay,
Brings that high impedance
down,
to.
down. And why is it high impedance there? It's not infinite, but still you've got, if your wavelength is here and here, okay,
Because you've moved away from a low voltage, high current point to a higher voltage, lower current point on the antenna.
okay. And that's going to change with frequency. Okay. Another way to do it is, you know, I hate to harp on this open line thing, but you wonder why the old folks run a lot of open wire stuff, you know, because you don't worry about the SWR here. You put the matching network in the, we didn't call them antenna tuners back then, we called them matching networks, you know. You'll find a lot of them, a lot of the older ones.
The question I have is on an off-center FET, does both the longer portion of the dipole and the shorter portion of the dipole radiate? And do they do so with different efficiencies at different frequencies? Because it seems to me that's how it gets some of its flexibility on the bands.
I know if I flop the wires around and put the hot side on the shorter end, it doesn't work near as well.
Okay.
But I don't know enough about what to do with a matching network to really answer that question.
Okay.
But that is going to impact your radiation. Okay, we talked, what did we call this wave back a while ago?
Sine wave.
Sine wave, okay. And what's the light, our radio waves, what are they made of? What do we call them? Electromagnetic wave. And that includes light, includes our radio waves, up and down the frequency spectrum. Electromagnetic. There's an electric field and there's a magnetic field. And they run orthogonal to each other, 90 degrees out of whack. Okay, so electrical field, if it's vertical, then the magnetic field is horizontal. Am I running into your time?
Very good.
So if the electric field is vertical, how do we say the wave is polarized? Okay, think about a vertical antenna. Vertical antenna. Which way is the current flow? Current flows up and down. Vertical. It's vertically polarized. It depends upon the electric field. The polarization is determined by the electrical field. So vertical antennas tend to be vertically polarized. Horizontal antennas, your current flow is horizontally. What happens now out in the ionosphere? It becomes all, that's one way to put it. Okay.
Quantum effects.
Okay. How do polarized sunglasses work?
By only allowing light with a certain polarization through.
Exactly. Glare tends to be horizontally polarized. So if you look at the pair of sunglasses, the filter allows vertically polarized rays through, not the reflected glare. And same thing, your antenna, if you got a vertical antenna, works better with vertically polarized radio waves. It could work the other way, but you've got substantial degradation. You also got circular polarized, which most of the satellites are running.
Which is why you should not use a vertical antenna on 2 meters to work single side band. most people are using horizontally polarized antennas.
That's right, and that's more important on the VHF, UHF, because it's line of sight, whereas HF and stuff, you've got people all over the place. You've got people running, you know, vertical. I'm running a vertical. I got vertical polarization, at least when it leaves the antenna. I talk to Europe all the time, and one guy's running 6/6 on 20. It's specifically horizontally polarized when it leaves the antenna, but in the ionosphere, it tends to get, okay? So, I think I've about covered everything. But a few things to keep in mind, a few things to talk about your new hams. Yes, sir.
The vertical horizontal thing is true once your signal gets up into the atmosphere. We run a 10-meter net in Zephyr Hills. And there are people within a mile of me that I cannot pick up with my horizontal inverted L is what it
Yeah.
by the time I get done with my small lot. I can't pick him up. But I can get anywhere, 44 countries and all that with the wire, but I can't get across the street on 10 meters when he's running vertical. So,
Does he get you when he's running horizontal? Does he receive you when you're getting when he's running horizontal as well?
he doesn't have one.
He doesn't have one. Okay. Two.
I found this out back in the old CB days, because I had a Supermag going up through a 3-element horizontal beam.
Uh-huh.
And on the horizontal, I could get out 65, 85 miles without any trouble, 5 watts, playing it legal. And then, but you could cut out all of the local noise with the horizontal, all that local stuff. And then bring it back with the vertical and get across the street.
Yeah. Speaking of noise, vertical antennas tend to be noisier than horizontal antennas, as a general rule. They are there. Yeah. So, I about out of time.
That's it.
Okay. Thanks, folks. I'll be around here for a little bit. I got a couple cards here. If anybody wants a card, I'm glad to talk to anybody anytime about stuff, even if I don't know what I'm talking about. Well, not really, but that takes me back to one of the questions somewhere on there. You'll say is, you don't want to talk to the guy that says, I don't know, but I'll tell you. So I don't really do that. But I'd be glad to. And a lot of this is have an idea of where to find the answer, who to talk to, what book to look at. If you're really basic and need the basic of electronics and stuff, the basic book from ARRL is excellent. I used it to teach a college class. It is excellent. The basic wires. Thanks much for your time. If somebody wants to